Okay, I am sharing the screen, but it got stuck. Okay, so today we are actually going to talk about two applications of divide and conquer, which are to do with more mathematical applications. So one is going to be normal integer multiplication, and one application is going to be matrix multiplication. So two kinds of multiplication we'll be looking at. All right. Hopefully it should work now. I have started it. So hopefully you can share this, see the screen now. There is some delay, but hopefully it will work. Okay, good. So let's go through, as I said, the first problem that we are going to look at is integer multiplication. So basically, whatever we used to do, like, multiply two number, 232, 434, whatever, 8, 2, 9, then 8 to 9 again, and then 8, 8, 6, 0, 1, whatever. I mean, so this is what. So what we used to do that there will be these. So suppose we are multiplying two n digits, and what is these n partial products, right? We need to sum them up to get the result. Similarly, the same thing can be done in like binary also. So 10100, whatever, 1100, and then you whatever put. Then you sum them up. Whatever. So you get this, but again the same thing. If there are two numbers, n digit, n bit numbers, then you get n partial products, and then you sum them up to get the result. How much time will it take to get one partial result? These partial product. We take one digit and make with this number. So how much did you get one partial product? Am I audible?
Yes, sir.
Sir, your voice
Yeah.
is
So how
breaking.
much time will it take to get one? Okay. Let me see. Is it better now?
Yes,
Okay,
sir.
I get that it was breaking. Is it better now?
Yes, sir.
Even now it's bad?
It's fine
Is
now.
it better now or not? No?
Yes, sir. It's better.
It's good.
I switched off my video. It's better? Okay. Cool. Can you hear me now?
Yes, sir.
Okay, good. Thank you. So my question was that, okay, we get n partial products. So how much time does it take to get one partial product? So there are these. So for getting each partial product, what do we have to do? We take this number and we multiply one bit or one whatever digit of the number to this, the top number. So how much time does it take to get one partial product?
The number of
You multiply
digits.
the number of digits. So one partial product will take, let's say, order n time, because basically it will be order n many multiplications, right? And there are n of them that you need to sum up. So you obtain the first one in order n time, then you obtain the other one in order n time, then sum it up, and the summation will take order n time, right? Because there are n digits to be summed up, and so on, right? So how much time it will take in total? So basically, for each of the partial sum, you are spending 2 times, or basically order n time. Order n time to compute for computing it, and order n time for summing it up to the whatever sum you have right now. And then you calculate the next one, order n time, sum it up. So this is calculation, and then order n time to sum it up to whatever you have already, and so on. So here, there also you spend order n time, and this you will do. There are n partial products, so this whole thing you will do n times. So total you get order n square time. Right? So is this clear? But this is an iterative algorithm. We have not really exploited divide and conquer. Is this clear why this takes order n square time, or if there is any confusion, please ask.
Sir, it's clear.
Okay, let me try to turn on the video and see, like, in case that helps, like, understanding what I'm saying, if you can see me. All right. And if this worsens the voice or anything, please let me know. Okay, good. So, all right. So now we have to, let's see how can we do it recursively by doing a divide and conquer kind of approach, right? So suppose it does not matter which base we are going to use, but let's say that suppose we are using base 2. Okay. And suppose the numbers are x and y, n bit numbers, and let x is equal to 2 to the n over 2, x1 plus x0, right? So that is the x1 is the first half of the most more significant half of the number x, and x0 is the less significant half. And y is equal to, again, I'm assuming that these are even, because that is not going to make much of a difference, right? So what is going to be xy? What is the number that we want to compute? X1 Okay, so I'm directly going to write like instead of x1, y1 2 to the n plus x1, y0 plus y0, x1 2 to the n over 2 plus x0, y0, right? So I just multiplied these two. So now, what does it mean? That means that, okay, now if we want to do divide and conquer, what will we do? We basically compute these terms recursively. x1, y1 we compute x1, y0, y0, x1, and x0, y0. We compute them recursively. And how many bits does x1 have?
Sir, n by 2.
N by 2. So all of them. Y1 is also n by 2. So all of them have n by 2 bits. So all these multiplications, the recursive multiplication that we are going to do in the recursive step is multiplying two numbers and over 2-bit numbers, right? And then after we get the summation, what do we have to do? We have to do 1, 2, 3 summations. And basically just multiplying by 2 to the n is just adding zeros. This is also just adding zeros, so that will not affect much. So basically you get 3 additions. So order n time to add numbers up. So what is the recurrence that we get? Tn is equal to 4tn by 2 plus order n, right? And what will this solve to from what we have seen in the class?
Sir, order n square.
This will solve to order n to the log 2 base 4 is equal to order n square. Okay. Good. So we did not achieve much. We already had an order n square algorithm, but we again got an order n square algorithm even after doing this divide and conquer, right? So what's the use? So actually what we would like to get, suppose if we, instead of 4 recursive computation, if we could do 3 recursive computations, then the running time we would get will be Tn is equal to order n to the log 2 base 3, and that will be better, right? We had seen that that is 1.59. Okay. So how do we do that? How do we do it in now like 3 recursive calls? So let's look at what do we want to compute. We want to compute again, let's say x1, y1, 2 to the n, plus x0, y1, plus y0, x1, 2 to the n over 2, plus x0, y0. This is the number that we want to compute. Now, what is the trick here? So you have to apply some trick. That consider this number, x0 plus x1 times y0 plus y1. Okay. So what do you get then? You get x1 y1 plus x0 y1 plus y0 x1 plus x0 y0, right? So if we compute this number, and this number will take just one multiplication, right? Why? Because this is 2 to the n over 2, this is 2 to the n over 2, you sum them up, this is 2 to the n over 2, this is 2 to the n over 2. This is one multiplication of n over 2 bit numbers. So can somebody like think that if we have this number, then how can it help us in reducing the total number of multiplications?
We will compute x
Here-
y1
here-
and x0 y0 anyway, so we can subtract it.
Exactly. So we'll compute x1, y1, x0, y0, and this number. And then we can subtract the summation of these two from this number to get the middle term. So in total, we get 3 recursive calls. So let's call this number z, for example. Okay. So what am I saying? Compute z, compute x1, y1, x0, y0. So this is the 3 recursive calls, right? And then for how do you output your number? For outputting the number, you output whatever x1, y1, 2 to the n plus z minus x1, y1 minus x0, y0 2 to the n over 2 plus x0, y0. Right? And this number is exactly what we want here. Right? So what is the time complexity now? So again, the addition and the adding of zeros and the addition will again take the same time, and even this subtractions will again take linear time. So what is the time complexity of this one? It's Tn is equal to 3Tn over 2 plus order n, exactly what we wanted. So Tn is equal to n to the log 2 base 3. Okay. So the trick was that we get these explicitly and then we compute this sum, which actually basically contains all the terms. And the thing was that we needed some of these two terms. We did not need these two terms separately. So now the thing was that okay, anyway, you need them separately, then why calculate them, together, why calculate them separately? Calculate the other terms separately and then subtract to get the sum of these two terms. Okay. Any question for this? It's okay. Okay, good. Now, similar thing, suppose we want to do in case of matrices, okay? So, matrix multiplication. So, suppose we have two n cross n matrices, A and B, and we want to find A times B. Okay, so now since they are n cross n word matrices, and suppose this is the C that we want to find. So C has how many entries? How many entries does C have?
n square.
Right? N square entries. How obtain one entry of C? So suppose you want to obtain Cij. How do you obtain that?
So multiply ith row of A with the jth column of B.
Ith row of A with jth column of B, right? So Cij, ith row of A with jth column B, you multiply, and this multiplication will, okay, so this is a row matrix, this is a column matrix of, size cross n cross 1. And so how many multiplications will this take? How many multiplications and how many additions?
N multiplications, N additions.
Yeah. N multiplications and N additions. So order N. And since there are N square entries, how much time will it take? Order N cube time. Okay. Is that clear?
Yes, sir.
So
Okay. So now again, this is again a very iterative algorithm that okay, we go through this entry by entry of C and calculate that using the rows and columns of A and T. Okay. So all right. So what do we do now? How do we apply divide and conquer here, right? So let's divide the matrix A and B into like these parts. C also, right? So let's say A is equal to A11, A12, A21, A22. Okay. So then can we say about these matrices, that what they will be in terms of products of submatrices of A and B? So what can we say about C11? So these A11, A12,
plus A21 B
say again, sorry, I missed it.
A11 B11 plus A12
Yes.
B21.
A11, B11 plus A12, B2, right? So this is what we get. So again, since we want to do divide and conquer, let's put this n by 2, right? Similarly on this side also. So all these matrices are n by 2 cross n by 2 matrices, right? Good. So similarly, let's write down for all of them. So C12 will be A11, B12. If I make a mistake, please tell me, okay? Because I might doing it A11, A12, B22, C21 is equal to A21, B11 plus A22, B21, and C22 is equal to A21, B12 plus A22, B22, right? So this formula, again, if there is a mistake, like let me know. But is this formula is correct? Like then it gives us a recursive way to compute C, right? So how do we compute C? Compute C11, C12, C21, C22 recursively. Right? I mean, the not by computing these guys, and these guys will now involve. So compute all these. And how do you compute C11? C11 you compute A11, B11 by using the same matrix multiplication algorithm. And then you also A12, B21 again, and then summing them up. So summing them up will take how much time? What is the dimension of A11, B11?
N by 2 cross N.
N over 2 cross N over 2. So how many entries do they have? n square by 4. So how much time will it take to compute them? Compute the sum of two of them?
Order n
Sir,
square.
order n square.
Order n square time, right? So summation will be order n square time, right? So once you sum these up, then you get one part of C. Similarly, you have these four parts, right? So what is the recurrence that we are going to get?
Sir,
Can
8
someone
times
tell?
d n by 2 plus order n square.
Right? Because for each one of them, you get two multiplications, right? And for the summation, you get n square. And again, you have four such summations, right? Okay, and this we had not seen this in this form, but if you solve this, this will also come out to be order n to the log 2 base 8 is equal to order n cube. Okay. So again, we did not end up gaining much. But now the question can be that can we do something similar, some such trick as we did in case of integer multiplication, right? That okay, is there some product or is there some partial sum that we we can calculate using the other ones and so on, and it does not seem very trivial, but there is a way to do it, and that was the first algorithm which actually brought the bound below n cube. So this was the only algorithm known for quite some time for order n cube, and that was the again a trick which is there which brings it down from n cube, and it uses some similar thing. So till then, if there is any question from what I have done till now, please ask. I'll take a sip of water. All right. So this is Strassen's algorithm. So I hope there is no question till now. Good. So now instead of 8, we want to compute 7 products only. There's another thing, if you notice in the integer multiplication thing, is that even though we are calculating less thing, the total number of additions increased. Right? So you have an addition here, you have an addition here, you have this, and so on. Right? So that increased. So basically now you are spending more time in doing the spending less time in doing some recursive task, but while combining them, you are doing more effort. So something similar you want to do here also. That you want to compute 7 products only and then combine them to get whatever this C11, C12, C21, and C2, right? So combine them, meaning now again you want to add or subtract, whatever. Good. So how does Strassen do it? How did he do it? And it's actually, I mean, very. So basically, what he does is takes these some of the submatrices. So basically, he takes some partial products of the form whatever alpha 1 1 A11 plus alpha 1 2 or A12 plus alpha 13, alpha 21 A21 plus alpha 22 A22 times beta, let's say 11 B11 plus beta 12 B12 plus beta 21 B21 plus beta 22 B2. Okay, my beta and B look way too similar. Okay, so now what he does that he looks at this product and he fixes the values of alpha ij and beta ij from -1, 0, and 1. Okay. So the idea is that, okay, we want to, and also in this direction, there can be more general ways, but he does it in this direction because you don't want, like, you want to multiply AIs with BIs only. You don't want to, like, since matrix multiplication is not commutative, you don't want to be multiplying BIs with AIs. So these are the 4 submatrices out of which you want to calculate these, some kind of uh, partial things, which then you want to rearrange to get. So earlier, what did we have in integer multiplication? We took this x0 plus x1, and then we took y0 plus y1, right? So here he is doing that. Okay, let's take all these submatrices of A and then uh, add some coefficient, maybe 0, maybe 1, maybe -1, add them up. Then you take similarly for submatrices of B, add them up, and then get some partial products, and then try to combine them in some way. So I'm not going to get into details. If you want to read, like, more about the intuition of how he did that or how he might have done that, nobody knows how he did that. It seems like magic. But in CLRS, there is a slightly, like, detailed explanation of how you can arrive at what Strassen's algorithm is, or what Strassen arrived at. So I'm just going to describe it, and you can try to see that how it seems very magical. So he computes these 7 partial products, or 7 these matrices. So call them P is equal to A11 plus A12, sorry, A22. I have to be careful. B11 plus B22. Q is equal to A21 plus A22 times B11. R is A11 B12 minus B22. S is equal to A22 B21 minus B11. T is equal to A11 plus A12 times B22. U is equal to A21 minus A11 B11 plus B12, and V is equal to A12 minus A22 times B21 plus B22. So this is what he did. That, okay, these are the 7 matrices that we compute, and for each of them, it will take one recursive call of the multiplication on n over 2 bits, right? And then what he says, let me just move it down. And then what does he say? He just says, okay, so now you want C11. C11 is going to be P plus S minus T plus V. He says C22 is, or C12 is R plus T. C21 is Q plus S, and C22 is equal to P plus R minus Q plus U. Okay. So let's just check some of these, like, just to go through that. Okay, what is going on? So this is P plus S minus T plus U. So let's do it here. So C11 it says is equal to P plus S minus T plus U. So what is P plus S? Again, if I make a mistake, please let me know. So P plus S is A11 B11 plus A11 B22 plus A22 B11 plus A22 B22 plus S, so plus A22 B21 minus A22 B11 minus T A11 B22 minus A12 and plus U. So plus A2 B11 plus A21 B12 minus A11 B11 minus A11 B12, right? So A11 B11 gets cancelled, right? Should A11 B11 get cancelled? I don't know. Then A11 B12 or A12 B11. A11 B11 should not get cancelled. I'm making some mistake. What is the last term? A2. Sorry, am I making some mistake here? T plus U. T plus V it is. Sorry, this is not U. That is the mistake. So let's do plus V. So plus V is going to be plus A12 B21 plus A12 B22 minus A22 B21 minus A22 B22. Right, good. So plus A22 B22 minus A22 B21 should also get cancelled somewhere. Minus A22 B21, A22 B21. A12 B22 should be there, I guess. A12 B21, A12 B22. A11 B22 gets cancelled. A22 B11 gets cancelled. And A12 B22 gets cancelled. So all you have is A11 B11 plus A12 B21. Right? Exactly what you want. Oops. All right. This one here. Okay. So similarly, so this happened for C11. And okay, we have some time, so we can check a couple of more. So this is what we wanted, like, C11's value, if you go check up, this is what C11 is. Now you want C12, let's say, is equal to R plus T. This should be simpler. So R plus T is A11 B12 minus A11 B22 plus A11 B22 plus A12 B22 and A11 B22 gets cancelled. So A11 B12 plus A12 B22, which is what is needed. So this is also fine. You get C12 also correctly. And let's see the next one, which is C21 is equal to Q plus S, it says. So what is Q plus S? Q plus S is whatever A21 B11 plus A22 B11 and plus A22 B21 minus A22 B11. So when this gets cancelled, it's equal to A21 B11 plus A22 B21. And that is what we want. And again, like you can verify that this also works out. So the point is that, okay, what is happening here that now what is the algorithm? Matrix multiplication. It takes two matrices A and B. And what does it do? It first, compute whatever P is equal to, or let's say this A11, A12, A21, A22, B11, so on, all these. Then what does it say? Compute E is equal to matrix multiplication of A11 plus A22, comma B11 plus B22. Similarly, Q is equal to again matrix multiplication of something, R is equal to something, S, P, U, V. Right? So there are these 7 matrix multiplications that will be computed, and then what will it say? That okay, fine. Now C11 is equal to whatever, C12 is equal to whatever. These summation and like these formulas. That's it. So how much time does it take? So there are these 7 recursive calls. This will take linear time, of course, and all these will take n squared time. Because this is just some addition and subtraction of n bit, n cross n bit matrices, right? So what is the recurrence that we get? Anyone?
Order
70.
n to the power log to 7.
Oh, like recurrence is 7 times tn by 2 plus order n square.
This will solve to, again, you can see how to solve it, and this will solve to order
N to the power log 7 base 2.
n to the 2.81. Okay. So this was and matrix multiplication is something that is like used widely, among like too many applications, and it has, and so this was the first like breakthrough below. And can you imagine what would be a lower bound for matrix multiplication? How many operations will it need, or should it need at least to compute matrix multiplication? Any trivial lower bound, anything. Yeah. Yes, Nikhil.
Sir, order n square at least, because there are n square terms.
So let's not say order n square, let's say omega n square it will need, right? Because we are talking about
Right, yes, sir.
lower bounds. Because C has n square entries. At least you need n square time, right? Because you need to at least write down, you need to at least figure out each element of C. Right? So, and there is actually no progress made on this lower bound till now. We don't know any way to show that actually matrix multiplication will take more than n square time. And for a long time, this gap was n square and n cube. Then Strassen came and he dropped it to n to the. So I don't know whether you can see this. So this was Strassen. So it was at 3. And then Strassen came, he brought it to 2.81. Then again, some more progress, and it kept decreasing. So this is on x-axis, I think, no, on y-axis, I think there is time. And right now, this is Virginia Williams and Alman's result, which is there. And she even previously had this bound and so on. And right now, it's, I think, 2.8, 2.23. Okay, let me check.
2.373.
Yeah, it's not 2. Yeah, so it's 2.3728. And now the, like, all the race is going on that after this 8, so they are decreasing at 4th, 5th places and so on, these numbers. But still, the problem is so important and so widely used that even decrease of a little bit there is considered a huge result, and so on. So, I mean, this is just to motivate you that a lot of work has been going into, and now people are thinking that the only incremental results are coming. So this approach, whatever they were doing, might not take us to this holy grail of m square. That is the only lower bound that we know. So yeah, that was it for today's lecture. Any questions?
Sir, for normal multiplication also have
Okay.
been like there have been lower bounds.
For normal?
Sir, for normal
Integer
multiplication, not
multiplication.
matrix. Yes, sir.
Yeah, integer multiplication, right? Integer multiplication, I'm not aware of, at least. That's a good question. I'm not aware of. I mean, one, again, of course, there is one lower bound that is order n, because there are going to be order n bits, whatever 2n bits there can be, but I'm not aware of any non-trivial lower bounds. There might be, but that's a good question. I don't know. Maybe I can look it up. Okay. Any other question? So generally, these lower bounds are very hard to obtain. That is why the only lower bound we have is trivial one, right? And I mean, because the lower bounds have to be like imagination proof, like that. Okay, somebody should not be able to break it by just doing something clever or whatever. So basically, they should work against every possible algorithm that has been thought of and that has not been thought of. So that is why generally the lower bounds are usually trivial in nature, but like when they are not, they are like they generally give a huge insight into the problem also. So that's another theory. Like in this course we'll be mostly doing algorithms. We'll be doing some conditional lower bounds later in the course, like when we see NP completeness. But yeah. So good. If there are no further questions, then see you guys on Thursday. And thank you for coming. And sorry for being late. And yeah, hope you got what I wanted to do. Thank you, sir.